Welcome to the final topic of the Matter and Energy Unit, calorimetry. Calorimetry is an extremely useful technique, and if you're fortunate enough to be in school at the time you're seeing this, you will likely be doing a lab or three on calorimetry. It's a wonderful technique. This technique is used to figure out how many calories are in your food. Yeah. See, this is what happens. Let's say you take a peanut and you burn it in a calorimeter. It's surrounded by water. This is what a calorimeter looks like. Your reaction takes place in this chamber. The reaction either absorbs heat from the water, causing the temperature to drop, or releases heat to the water, causing the temperature to rise. And by figuring out how much the temperature went up and how much water you used, you can actually calculate how many joules of energy were absorbed or released by this reaction. It's a wonderful technique. And let's say we do this and we're going to burn the peanut in order to get the calories out of it. Now, is burning a physical or chemical change? Well, of course, it's a chemical change because once you burn a peanut, you don't have a peanut anymore. I would recommend not trying this around anybody who has a peanut allergy. Number two, is the process of burning an exo or endothermic process? Well, burning causes the temperature to rise, which means heat is being released, so it's exothermic. Number three, will the temperature of the surrounding water increase or decrease? Well, when you burn, it causes the temperature of the surroundings to increase because the energy gets released to the surroundings. And number four, how does the combined mass of the peanut and oxygen needed to burn it compare with the combined mass of the carbon dioxide, water vapor, and carbonized peanut remnants produced by the reaction? Well, of course, the law of conservation of mass says that you cannot create or destroy mass. So the mass of the reacting substances must always equal the mass of the products that you form. Okay, with that in mind, let's look at heat of reaction. During a reaction, any kind of change, you can either lose potential energy or gain it. If you lose energy, that would be a negative change in heat. Delta means change, H means heat. Heat is another word for potential energy. So a negative change in heat. It's kind of like if I lose money from my wallet, that's a negative change in how much money I have stored in my wallet. This would be an exothermic change. The temperature will increase because the potential energy is being released as kinetic energy. Remember, when we burn an alcohol, the energy stored in the bonds in the alcohol is released to the outside, causing the kinetic energy, the temperature of the surroundings, to rise. And of course, the amount of energy lost and gained has to be the same. You can also gain energy. This would be a positive change in heat. Like if I was walking down the road and I found money and put it in my wallet, that would be a positive change in dollars. This would be endothermic because we're putting heat into it. Because we're taking energy that's out there and storing it, the overall temperature will decrease because if we take the surrounding kinetic energy, which is measured as temperature, and convert it into stored energy, well, there's less kinetic energy flying around, so there's less temperature. And of course, the amount of energy lost and gained has to be equal. That's going to be important for the math that we do, by the way. The kinetic energy lost equals the potential energy gained. So the formula we're going to use, this calorimetry equation, is going to have potential energy on one side of the equal sign and kinetic energy on the other side of the equal sign. So in an endothermic change, if you're in New York State, you can refer to reference table I. The reaction of nitrogen gas and oxygen gas produces nitrogen dioxide. This reaction has a positive heat of reaction, a positive delta H. That means that energy is stored in this reaction. Whatever energy N2 and O2 had, NO2 has 66.4 more kilojoules of energy stored in it than the starting materials, the reactants, had. So overall, we have an increase of 66.4 kilojoules of energy. Since potential energy increases, that means kinetic energy decreases. That's right. And because we have less of what temperature measures, we'll have a lower temperature as well. That would be an endothermic reaction. Here's an example of an exothermic reaction. When we take lithium bromide and dissolve it in water, it ionizes into lithium ions and bromide ions, both aqueous. What does that mean? That's right, mixed with water, dissolved in water. But this has a negative heat of reaction. That means that whatever the amount of energy stored in lithium bromide is, there's 48.83 less kilojoules stored in the products. That means potential energy decreases. And if potential energy decreases, that means kinetic energy, that's right, increases. And because temperature measures kinetic energy, more kinetic energy means more temperature. Now that we've got the basics out of the way, let's figure out how we figured out those numbers to begin with. We use a device called a calorimeter, which uses a measured mass of water. Each gram of that water heats up at a very specific rate called the specific heat. Each gram of water will heat up by 1 degree Celsius or Kelvin for each 4.18 joules of energy given to it. If you're heating up a different substance, every substance has a unique heat, a specific heat. What's more, every phase of a substance has a different specific heat. So this is for liquid water specifically. We can find this on New York State Reference Table B, the specific heat capacity of water, 4.18 joules per gram per either degree Celsius or Kelvin. Remember, a Celsius and a Kelvin degree are the same size, so you can use them interchangeably. This will result in a change in temperature. And what we do is we use a thermometer to measure that change in temperature. And this will give us three variables: M, which is the mass of the water, C, which is the specific heat of the water, and delta T, which is the temperature change of the water. And look at the units for specific heat. We have grams, which we're measuring, degrees Celsius or Kelvin, which we're measuring, and joules, which is our unit for potential energy. So how do we put this all together in a math equation that we can use? You can find this on New York State Reference Table T. There's your M, your C, and your delta T, and it equals the quantity of heat. Since you're left with joules, joules is a measure of potential energy, and as I said, another word for potential energy is heat, stored energy. So joules equals grams times 4.18 joules per gram, so grams have just canceled out, times temperature change in Kelvin, so Kelvin cancels out, meaning joules equals joules. So when we do this, we get the formula Q equals mass of water times specific heat capacity times change in temperature. Q equals MC delta T. I said MC delta T. I said MC delta T. That's calorimetry. Make sure you check out my video on YouTube called, what is it? What's the name of the video again? Oh, MC delta T. All right, so let's see. Yeah, you don't have to memorize it. It's right there on the reference table. Okay, so some example problems. A chemical reaction is carried out in a calorimeter with 125 grams, ooh, that looks like mass, of water. The temperature increases from 20 to 33.2 degrees Celsius. Ooh, that looks like a temperature change. How many joules of energy were released by the reaction? Well, Q equals MC delta T, and the mass of water is 125.0 grams, so we just substitute that in. The specific heat of water is 4.18 joules per gram, and it doesn't matter if you use Celsius or Kelvin, so let's just pop that in. And our temperature change, we go from 20.0 to 43.2, so that's a 23.2 degree temperature change. So we're going to plug that in for our delta T and multiply it out, and that gives us 12,122 joules. But you guessed it, We need to deal with significant figures. So our first number has 4 sig figs, 3 sig figs, 3 sig figs. We always go with the fewest sig figs. 1, 2, 3. We round it off to the nearest hundred. 12,122 to the nearest hundred is 12,100 joules. So rounding, this is your first practical application of the use of rounding. If you just heard that weird sound my microphone made, my cat, who has a stubby little tail, just walked by my microphone. Oh, he's doing it again. Yep, there he just did it again. It's 3:30 in the afternoon, and it's time for him to have his dinner. Well, he's just going to have to wait until I finish. I'm sorry, buddy. This won't take much longer. Okay. A chemical reaction is carried out in a calorimeter. The temperature increases from 22 to 35.8 degrees Celsius. Okay, so we have a temperature change. It looks like 13.8 degrees. That's good. 8,000 joules of heat is added to it. Okay, so we know what the joules are. How many grams of water are in the calorimeter? Now we're being asked to solve for mass. So remember when I taught you how to do the algebra? What we do is we put a circle around the mass and we rearrange the equation to solve for m. So we divide both sides by c delta t. Once we have a rearranged equation, we just simply substitute in the numbers. Our Q is 8,000 joules, so we plug that in. Our specific heat is 4.18 joules per gram degree Celsius. We substitute that in. And as we said, our temperature change is 13.8 degrees Celsius. We substitute that in. Joules and degrees Celsius cancel, leaving us with grams. How many sig figs? Well, 8,000 joules has 4 sig figs because it's a decimal point. 4.18 has 3 sig figs. 13.8 has 3 sig figs. So I guess we need 3 sig figs. Let's count in 3 sig figs, round it off to the nearest ones. Of course, the 6 in the next place rounds you up to 139 grams. So we've solved for Q and M. That leaves us to solve for delta T. A chemical reaction is carried out and water has 85 grams of water. That's our mass. The reaction releases 4,500 joules of energy. I guess that's our Q. What is the temperature change? Well, this time we're going to have to solve for delta T. In order to do that, we divide both sides by MC. Then we can substitute and solve. 4,500 joules is, I have claws in my back. Sorry about that. 4,500 joules. I even include the decimal point so I don't lose on my sig figs. The mass is 85. Oh, sorry, we're doing specific heat. My bad. 4.18 joules per gram degree Celsius. We'll substitute that in. Our mass is 85.0 grams. We substitute that in. 0.0 in grams together. Now, when you plug this in your calculator, remember it's 4,500 divided by 85 divided by 4.18, because that's the only way your calculator knows that they are in the denominator. When you plug this in, your joules and grams cancel, and you get this. Now, how many sig figs? 4,500 with a decimal point is 4 sig figs. 85.0 is 3 sig figs. 4.18 is 3 sig figs. So we count in 3 sig figs, but note there's a 6 in the next place, which will round 12.6 to 12.7 degrees Celsius. Now we can take this one step further. What if the question asked us, if the temperature started at 20 degrees Celsius, then what's the final temperature of the water? Well, if we add heat, our temperature will rise. So if we started at 20 and it rose by 12.7 degrees Celsius, well, then our ending temperature would be 37.7 degrees Celsius. However, let's just suppose that heat was removed and we started at 20 degrees. Well, if we remove the heat, then the temperature will drop by 12.7 degrees Celsius, leaving us with a lower temperature. What if it's not giving us the starting temperature? What if it says we are ending at 50 degrees Celsius after we added heat? What was the starting temperature of the water? Well, the temperature changed by 12 degrees Celsius. If we added the heat, that means the original temperature was 50 degrees minus 12.7. The original temperature was lower. So we subtract the heat, the temperature rather, and that gives us our starting temperature. If it says we ended at 20 degrees Celsius by removing heat, that means our original temperature was higher because it ended at 20 by removing heat. So originally the temperature was higher. How much higher? Well, in this case, 12.7 degrees higher. So we add them to get our starting temperature of the water. And these are all the practical ways that you can use the calorimetry equation, Q equals mc delta T. So don't forget to check out that music video by the same name, mc delta T. Enjoy and have a wonderful day. And as always, bye.